Late last year, the company behind Claude signed one of the largest compute deals in AI history, up to 1 million chips, worth tens of billions of dollars. And not one of those chips comes from NVIDIA. They come from Google, because this is not a graphics card and it's not a server rack. It's a machine that fuses 9,216 chips into one giant computer, moves data on beams of light, and rewires itself in real time. And when a report leaked that Meta might be next in line, NVIDIA lost over $100 billion of market value in a single day. And for the first time in years, felt forced to publicly explain why it is still ahead. This is the story of the machine NVIDIA feared the most, and of the 10 quiet years it took Google to build it. Subscribe to the channel and let me explain. To understand what Google actually built, we have to go back to 2013, long before ChatGPT, long before the GPU shortage. Back then, Google ran an internal projection that scared them. Speech recognition was finally starting to work, and the math showed something brutal. If every Android user talked to their phone for just 3 minutes a day, Google would have to double its entire data center footprint. Double it. For one single feature. Running neural networks on ordinary CPUs and GPUs was simply too slow and too expensive at Google's scale. So they made a radical decision: stop relying on general purpose hardware and design a chip that does one thing extremely well: the matrix math at the heart of every neural network. That chip became the tensor processing unit. And the first version went from design to running in Google's data centers in about 15 months, which in the Silicon world is almost unheard of. By 2015, it was quietly working in production, accelerating search and speech. That first version could only run neural networks, not train them. But in Google's own tests, it delivered an order of magnitude better performance per watt than the CPUs and GPUs of that time. And nobody outside the company even knew it existed. And then came March 2016. AlphaGo against Lee Sedol, one of the greatest Go players in history. Millions of people watched a machine outplay human intuition for the very first time. And almost nobody asked what hardware it was running on. Well, it was running on TPUs. The first public demonstration of Google's secret silicon was hidden inside a board game. From that moment on, Google shipped a new generation every couple of years, and each one solved one specific problem. The second generation didn't just run neural networks, it could train them, and it connected hundreds of chips into pods. The third generation moved to liquid cooling years before the rest of the industry was forced to follow. The fourth generation, in 2021, scaled to 4,096 chips and introduced a strange new technology we will talk about in a moment: optical circuit switches. The fifth pushed toward 9,000 chips per pod. Trillium, the sixth, doubled down on efficiency. And that brings us to Ironwood, Generation 7. So here is the part most people get completely wrong. Ironwood is not Google's panic response to NVIDIA. It is step 7 of a plan that started when nobody was watching. And that is exactly what makes it so dangerous. Google introduced Ironwood in April 2025 and called it the first TPU for the age of inference. And that framing matters because the industry is shifting. For years, the race was all about training giant models. Now those models are deployed to hundreds of millions of people, and reasoning models burn through compute at runtime thinking before they answer. Inference is exploding. And Ironwood was built precisely for that world. By the end of 2025, it was in customers' hands, and since this spring, it has been generally available to anyone with a Google Cloud account. So let's look at what one of these chips can actually do. A single Ironwood chip delivers 4,614 teraflops of FP8 compute. NVIDIA's flagship Blackwell chip, the B200, delivers about 4,500. Just think about that for a second. For the first time in this entire race, a Google chip beats NVIDIA's flagship GPU on raw compute. Only the GB200 superchip configuration stays slightly ahead at around 5,000. On top of that, each Ironwood chip carries 192 gigabytes of high bandwidth memory with roughly 7.4 terabytes per second of bandwidth. And memory bandwidth, not raw compute, is what actually decides how fast a giant model responds to you. Compared to Trillium, just one generation earlier, Ironwood delivers more than 4 times the performance per chip. That is not an upgrade. That is a leap. But here's the thing. Comparing single chips completely misses the point because Google doesn't think in chips. Google thinks in systems. So let me walk you through how this machine is actually built, because the architecture is where it gets wild. It starts small. 4 Ironwood chips sit on one host. 64 chips form a cube. And inside that cube, the chips are wired as a 3-dimensional torus, which means every chip talks directly to its neighbors, left and right, up and down, front and back, with no network switch in between. Data hops from chip to chip at 1.2 terabytes per second per link. There is no middleman, no traffic jam, no unpredictable delay. And for AI, this shape is a perfect match because training and inference constantly synchronize data across all chips at once. In a torus, those communication patterns map beautifully onto the hardware, and performance becomes almost perfectly predictable. Then Google takes 144 of these cubes and fuses them into one superpod. 9,216 chips acting as a single machine with 1.77 petabytes of shared high bandwidth memory and 42.5 exaflops of FP8 compute. To put that memory number into perspective, if your gaming PC has 32 gigabytes of RAM, you would need more than 50,000 of them to match one pod, one computer, the size of a data center hall. And this is where Google made a claim that went around the world, that one single superpod delivers 24 times the compute of El Capitan, the fastest supercomputer on Earth. Now here I have to slow down because this comparison is not fair. El Capitan is measured in FP64, the ultra-precise math you need to simulate nuclear physics. Ironwood is measured in FP8, the compact math you need for AI. It's like comparing a sprinter to a weightlifter. Both are extreme athletes, but they are not competing in the same discipline. So no, this machine is not 24 times El Capitan in any scientific sense. But strip away the marketing and the fact remains. A single superpod is still one of the most powerful computing systems humanity has ever assembled. And it exists for exactly one purpose: intelligence. Now to the part of this machine that feels like science fiction, the part I promised you at the beginning. Between those cubes, there are no ordinary network switches. There are optical circuit switches. Inside these boxes are arrays of microscopic mirrors, MEMS devices, and instead of receiving data packets and forwarding them, these mirrors physically steer beams of light from one fiber to another. Think of it as an old telephone switchboard, except the operator works in milliseconds and the cables are pure light. And this changes everything about how you run a data center. When a chip dies, and at this scale something is always dying, the mirrors tilt, the light bends around the dead hardware, and the machine heals itself. When a customer needs a different network shape, say a specific topology for a mixture of experts model, the mirrors tilt again and the cluster reconfigures. No human walks down an aisle. No cable gets touched. The machine is literally rewiring itself while it runs. And because a mirror simply reflects light, this layer adds almost no latency and consumes almost no power. Meanwhile, NVIDIA connects its GPUs through layer after layer of packet switches. Flexible, yes, but every layer adds electronics, heat, latency, and cost. Google replaced entire layers of electronics with light. And there is one more twist here, and it's my favorite one. The physical layouts of the last 3 TPU generations were partially designed by AlphaChip, Google's own reinforcement learning system. Just imagine, AI is now designing the chips that will train the next AI. The loop is closing. The whole system is liquid-cooled, and dedicated sparse cores accelerate the recommendation and embedding workloads that quietly power search, ads, and video feeds. And if 9,216 chips are not enough for you, Google's Jupyter data center network can link superpods together into clusters of hundreds of thousands of TPUs. That is the machine. But a machine, no matter how impressive, is just a spec sheet until someone bets their company on it. So the real question is, did anyone? Here is your answer. In October 2025, Anthropic, the maker of Claude and one of Google's most direct competitors in the model race, committed to up to 1 million TPUs in a deal worth tens of billions of dollars, with more than a gigawatt of capacity coming online in 2026. Just think about what that means. A frontier lab that competes with Gemini every single day decided to train and serve its future models on its competitors' silicon. Google Cloud's CEO explained the decision with two factors that should worry NVIDIA more than any benchmark: price performance and efficiency. Not hype, economics. And Anthropic wasn't done. In April 2026, they expanded the partnership together with Google and Broadcom. Multiple additional gigawatts of next-generation TPU capacity, reportedly around 3.5 gigawatts, coming online starting in 2027. Anthropic called it their most significant compute commitment to date, with the vast majority of that new capacity being built in the United States. And you can see why they need it. Their revenue run rate exploded from about $9 billion at the end of 2025 to over $30 billion today. One of the fastest scaling companies in tech history is feeding its growth with Google's machine. Then came the second proof point. In November 2025, Google released Gemini 3, and it shot straight to the top of the major benchmark charts. That model was trained entirely on TPUs. The model leading the leaderboards was created without a single NVIDIA GPU. For more than a decade, the rule of AI was simple. If you want the frontier, you buy NVIDIA. Gemini 3 broke that rule in public. And then came the moment the fear became measurable. On November 25th, the information reported that Meta, one of NVIDIA's largest customers, a company pouring tens of billions of dollars a year into AI infrastructure, was in talks to put Google's TPUs into its own data centers starting in 2027, and to rent TPU capacity from Google Cloud as early as 2026. To this day, none of it is officially confirmed. It didn't matter. NVIDIA's stock dropped about 4% on that single report, erasing over $100 billion of market value in one trading day. And then NVIDIA did something it almost never does. It published a public statement congratulating Google on its success while insisting that NVIDIA remains, quote, a generation ahead of the industry. And maybe that's true, but when the most valuable company in the world feels the need to explain why it is still winning, something fundamental has shifted, and the supply chain suggests this is only the beginning. Reports around Google's Cloud Next conference this spring point to shipment projections of 4.3 million TPUs this year, 10 million next year, and more than 35 million in 2028. Broadcom has reportedly signed on as a design partner through 2031, with MediaTek joining for a second chip line. And zoom out, and you see the bigger pattern. Amazon is scaling its Trainium chips. Anthropic runs on those too. Microsoft is building Maya. And Meta is developing its own MTIA silicon. Every one of NVIDIA's biggest customers is building an escape route. To be fair, this road is brutally hard. Tesla tried it with Dojo and shut the project down in 2025. Custom AI silicon eats companies alive, which makes 10 years of relentless TPU execution look even more remarkable. So, is NVIDIA finished? Not even close. And now we have to be fair to NVIDIA because their fortress was never just made of silicon. It is made of software. CUDA has been growing for almost 2 decades. Millions of developers write code for it. The critical libraries, CUDNN, NCCL, TensorRT, are the invisible plumbing of modern AI. and an NVIDIA GPU runs everywhere. In any cloud, in your own data center, in a university lab in the middle of nowhere. A TPU runs in exactly one place, Google Cloud. If you build your company on it, you are locked into Google and everybody knows it. Yes, the TPU software world, JAX and PyTorch has matured enormously. And the fact that Anthropic trains frontier models on hundreds of thousands of these chips proves the software gap is no longer a deal breaker. But CUDA is still a real moat. And here is an irony you simply cannot script. TensorFlow, Google's own legendary AI framework, is not supported on Ironwood at all. Even Google has moved on from its own past. We also have to get the system comparison right. NVIDIA's answer at rack scale is the NVL72. 72 Blackwell GPUs fused by NVLink into one compute domain. Some people frame this fight as 72 versus 9,216, and that framing is simply wrong. NVIDIA builds giant clusters by stitching thousands of racks together with high-speed switching fabrics. That is exactly how the largest GPU data centers on Earth work today. The real difference is philosophy. NVIDIA scales with flexible packet switch networks that any company can buy, assemble, and reconfigure however it wants. Google scales with a fixed torus and beams of light. More efficient and more predictable, but available from exactly one vendor in exactly one cloud. And on the roadmap, NVIDIA's GB300 and the upcoming Rubin generation will keep pushing per-chip performance forward. And let's not forget, demand for NVIDIA hardware still massively outstrips supply. Their chips are effectively sold out. Google isn't taking NVIDIA's revenue away, not yet. What's at stake is something subtler and, in the long run, far more valuable: inevitability. For a decade, every serious AI model on this planet had to be trained on NVIDIA hardware. That sentence is no longer true. And that leads us to the real race, the one that will decide the next decade. Because the strangest thing about this battle is that it is no longer really about speed. Look closely at the deals. They are not measured in chips anymore. They are measured in gigawatts. Anthropic's expansion alone is bigger than the output of a large nuclear power plant. Compute has become an energy problem, and this is exactly where Google has been quietly optimizing for years. According to Google, Ironwood is nearly 30 times more power efficient than its first cloud TPU from 2018, and roughly twice as efficient as Trillium just one generation earlier. When a single AI campus draws more power than a city, the question is no longer who has the fastest chip. The question becomes who extracts the most intelligence per watt, per dollar, per square meter. That is the metric the next decade of AI will be judged on. And that is the exact metric this machine was engineered for from day one. And Google is not slowing down. According to supply chain reports, the 8th TPU generation is already in the pipeline, and for the first time it splits in two. A training chip called Sunfish, co-designed with Broadcom, and an inference chip called Zebrafish, co-designed with MediaTek, both targeting TSMC's 2-nanometer process at the end of 2027. Which means the machine NVIDIA feared the most is only Generation 7. Generation 8 is already on the way. So here's where we land. NVIDIA is still the most valuable chip company in history. Its ecosystem is still unmatched, and it will very likely keep dominating AI hardware for years. But the era when the entire AI industry had no other choice, that era just ended. It didn't end with a dramatic keynote or a killer product reveal. It ended quietly, with mirrors, beams of light, and 10 years of patience. And here's the part I find most fascinating. The next time you talk to an AI, there is a growing chance that no GPU was involved at all. Now, I'm curious what you think. Will the biggest AI models of 2030 still be trained on NVIDIA hardware? Or does the future belong to custom machines like this one? Drop your take in the comment section below. If you enjoyed this episode, share it with someone who still thinks NVIDIA has no real competition. And subscribe to the channel for more stories like this one. Thank you for watching.